All right, guys, so we are going to learn a little bit more about two things called ions and isotopes. So we mentioned ions in our last lesson last week when we were talking about atoms that have charges, but I never mentioned a word called isotopes. And isotopes are similar to ions, but they've got a pretty key difference. So our goal today is explaining the difference between ions and isotopes. So as long as we can tell the difference between an ion and an isotope, we'll be successful. The way we're going to do this is by correctly determining the amount of subatomic particles in an ion and in an isotope. So ions and isotopes are particles, and subatomic particles means particles that are smaller than the atom, so particles within the atom. So we learned about three of them: protons, which have a positive charge, neutrons, which are neutral, and electrons, which are negative. And all three of these subatomic particles play a key role in identifying what's the difference between an ion and an isotope. So I've got a quick video right here that I'd like you to watch. This is going to give you a little bit more of an understanding of how does this apply in the real world. Am I ever going to see this ever again? So go ahead and pause this, take a moment to watch the Chernobyl clip. All right, if you're listening to me, then I'm assuming that you have paused, watched the video, and now you're ready to get started. So Chernobyl was a pretty big TV show that came out about a year ago, and it was all about this nuclear power plant that had a horrible disaster that exposed a lot of people to radiation, and there was a big cover-up. And then there was really a lot of problem solving done by scientists to solve this and figure this out. How do we keep people safe now that this has been exposed to the public and people are dying because of it? So in the video, you probably heard an explanation about how a nuclear reactor works that involved bullets. And bullets were an analogy for neutrons. So certain atoms are able to decay, is the formal word that we use for it. And what I mean by that is they're able to break apart into smaller atoms. And when they do that, they release neutrons that fire with high amounts of energy, making them a lot like bullets. And those bullets collide with other atoms, causing them to decay and rupture into two smaller atoms. And we produce a chain reaction that produces a lot of energy overall. And that energy can be harnessed for real world purposes, which is what a nuclear power plant is. However, when you don't contain that energy or that chain reaction, if you don't contain those bullets, they're very, very harmful to people because your atoms are not meant to decay and break apart. So firing bullets at them would be a very bad thing. What makes nuclear technology possible is isotopes. So a lot of our way of life, as far as like everyday things we take for granted, like heated water, lights, are due to isotopes. Arizona, in fact, is home to the second largest nuclear power plant, if I'm not mistaken, which is a pretty exciting thing. It's a pretty big deal, but there's a lot of controversy around it. And the more that you know about isotopes, the more informed of a decision that you can make when voting for things like clean energy. So we're going to move on, and we're going to start with an analogy about pizza that's going to help us understand isotopes. So our goal is to look at these three different pizzas and try to come up with a definition for what is a pizza. So I've got a single topping pizza, a deluxe pizza, and a mega pizza. I'm going to look and see what do these things have in common. So the single topping is round, has cheese and pepperoni. Deluxe is also round. It also has cheese, but it's got pepperoni and bacon. And then the mega pizza is round, has cheese, and has pepperoni, bacon, and ham. So it looks like all three of these are round and have cheese. So in order to be a pizza, it must be round and have cheese. But it looks like I can really have a variety of toppings and it's still a pizza. As long as I have at least one topping, it seems like, then I'm a pizza. The type of topping doesn't seem to matter, whether it's bacon, ham, or pepperoni. If you change the toppings, it just seems to change the type of pizza. So the topping determines the type of pizza. but it doesn't make a pizza. Pizza, I guess, determines the type of pizza. So if I wanted to tell the difference between one pizza and another, all I'd have to do is look at the toppings. But as I look at all of these pictures, they have a lot more in common than it seems like they have different. Really, the fact that they're round and they're cheese is what makes them a pizza. So I'm going to flip over to the next page. We're going to use this pizza analogy for isotopes. Sorry, it's lagging so much. So I've got 3 atoms right here, and they're drawn a little bit differently than what we've drawn in the past. I drew these with a little bit more of a ring model or a solar system model, like what Niels Bohr did, just because it's easier to represent. So you're going to see a variety of representations. Don't let it throw you off. It's still an atom. So I've got 3 different atoms right here with 3 different names. I've got carbon 13, carbon, oh, I'm so sorry, I read that out of order. Carbon 12, carbon 13, and carbon 14. So I'm going to figure out kind of what I did with the pizza. What do they have in common? What's different about them? So I can kind of come up with a definition for what the heck is an isotope. So carbon 12, I'm going to count how many protons it has. So carbon 12, I'm going to change colors here and use the red. In this drawing, my red particles are my protons. So if I count 1, 2, 3, 4, 5, 6, there are 6 protons. In carbon 13, I have 1, 2, 3, 4, 5, 6 protons. And in carbon 14, I don't even have to dot it out. I've got 6 protons. My electrons are going to be on the outside of the atom. So these are the black particles on the ring outside of the atom. And carbon 12 appears to have 6 electrons. Carbon 13 also has 6 electrons, and carbon 14 also has 6 electrons. So it seems like they have everything in common, but maybe something will be different when I get to neutrons. Now you might be wondering, how the heck are we going to figure out neutrons when they didn't give that to us in the picture? There's no drawing of neutrons here. I'm going to use the name of these isotopes to help me figure it out. Now, the difference in the names are these numbers, carbon 12, 13, and 14. So those numbers obviously have some significance here. They stand for the mass number, which is just the mass of the atom. And to refresh your memory, the mass number of an atom is equal to the protons and the neutrons added together, because the protons and the neutrons are the only subatomic particles with mass. Remember, those electrons are like your jewelry. They're so light that you don't even consider their mass when you're putting it on a scale. So if I have a mass of 12 and I have 6 protons, that must mean that I have 6 neutrons, because 6 plus 6 will get me a mass of 12. So carbon 13 must have 7 neutrons, because 6 plus 7 will get me a mass of 13. And then carbon 14 must have 8 neutrons, because 8 plus 6 will get me a mass of 14. So now I'm seeing finally that there's a difference in the parts of these atoms, and it's really those neutrons that are different from isotope to isotope. So if I wanted to write a definition for an isotope, a tentative one, mind you, because we're going to look at more examples, it seems like in order to be an isotope, you must have the same number of protons and electrons. Protons and electrons. And you must have different numbers of neutrons. Okay, so now that I've used the name to help me figure out the amounts of each subatomic particle, I'm going to represent each of these isotopes with something called a nuclear symbol. So we can go back and forth between the name and the symbol fairly easily. And we're really just talking about the same thing, the same atom of an isotope. So I could name this atom up on the top left here, carbon 12, or I could represent it with the nuclear symbol, which is just going to be the symbol of the element. In this case, we're referring to carbon. Sorry, it is really lagging. In this case, it is carbon. And I can put the mass number in the top left to say carbon 12. If I wanted to be extra specific, I could also put my atomic number, which is my number of protons, in the bottom left. And this is me being really thorough and putting all of the information in the nuclear symbol. Now, if I knew that the element was carbon, I could just look at my periodic table and see that it's element number 6 and realize, okay, so that means it has 6 protons. Its atomic number is 6. So I don't need to write 6 in the nuclear symbol as long as I have a periodic table. So if I were to do the same thing for carbon 13 and write the nuclear symbol, carbon is the element, and the mass number 13 would go in the top left. And once again, I could write 6 on there, but I'm not going to because I have a periodic table, so I can find out that carbon is element 6. And then last but not least, carbon 14, I could write as C with its mass number in the top left. And then that's just a lot less writing for me rather than writing out the whole name. So let's see if this definition we have of isotope is going to hold up when we look at some more examples. So I've got uranium right here, and you may be remembering that in the Chernobyl clip, uranium is the element that they use in nuclear power plants. It's a very specific isotope that they use, in fact. But there's a lot of different isotopes of uranium, in fact, out there in the world. So right now, we're looking at all of the possible isotopes that uranium can have. Uranium-232, 233, 234, 235, 236, and 238. Now remember, we said that in order to be an isotope, you had to have the same number of protons. So if I look at all of these isotopes, they all have 92 protons. So that holds up with my definition. 92 protons, 92 protons, 92 protons. And it looks like the other part of my definition, that they have to have a different number of neutrons, I did that in blue, is also holding up. I have 140, 141, 142, and 143. So it looks like my definition of an isotope is holding up. And if I wanted to write my symbol for all of these, remember, I could abbreviate this by just doing uranium and writing the mass number in the upper left-hand corner. I could also write the atomic number if I wanted to, but if I have a periodic table, my atomic number is going to be on that periodic table with uranium. So I'm not going to bother writing it down, knowing that I have a periodic table handy that I can refer back to. So let's look at one more example of isotopes and see if our definition holds up. So on to the next slide. It is really lagging. I apologize. My internet connection is weak. Beautiful. On to the next slide, we've got nitrogen. Now, nitrogen has 3 known isotopes. So our definition said that in order to be an isotope, there needs to be the same number of protons. And as I look at all 3 of these isotopes, they all have 7 protons. And this matches up with my periodic table. Nitrogen is element number 7, so it should have an atomic number of 7. It should have 7 protons. The other part of my definition is that my number of neutrons must be different. So as I look, 7 neutrons, 8 neutrons, 9 neutrons. This matches up. So nitrogen 14, nitrogen 15, and nitrogen 16 are all isotopes because they all follow that definition. They have the same number of protons. I'm going to write that in the corner. Same number of protons. And they have a different number of neutrons. As long as we're looking at atoms with the same number of protons and different number of neutrons, we are going to be looking at isotopes. So this seems simple enough. Isotopes are really about the protons and the neutrons. So let's see what ions are all about. So we're going to talk about the sodium ion. Sodium is the element Na on the periodic table. Now that might be kind of odd that sodium doesn't have a symbol with any letters involved in its actual name. And that's because sodium wasn't always called sodium. Once upon a time, it was called something else that involved an N and an A. And that's where the symbol comes from. There's a lot of elements on the periodic table that are like that, that have symbols that are a little bit unpredictable, but we'll just go with it. So sodium is element 11 on the periodic table. I've got the box drawn in the right-hand corner right here. That means sodium has an atomic number of 11, aka it has 11 protons. So in the nucleus of a sodium atom, if I were to look at the very center, I would see 11 protons, and those protons all are positive. So an atom of sodium has 11 positive charges. It's a lot of positive charges. Now, an atom of sodium is what we call neutral. That means it has no charge or zero charge. So if I have 11 positives in an atom of sodium, that must mean that I have 11 negatives, so that my charges perfectly balance out to zero. So I'm going to draw 11 protons, or I'm sorry, 11 electrons onto this atom. Now you may be noticing this is a little bit different than what we saw in the previous pages. This is a true solar system model. I'm going to speed through how to draw these correctly. There's a little bit of a system here. When you're drawing electrons on your rings, you always draw no more than 2 electrons on that first ring. No more than 2, that's the max. If you have more than 2 electrons to draw, then you move on to the next row. So I have 11 electrons to draw, so I've got 9 more that I still need to draw. On the second row, you can draw no more than 8 electrons. If you have more than 8 electrons to draw, 1, 2, 3, 4, 5, 6, 7, 8, then you've got to move on to the next row. So total, if I were to go back and count, I've drawn a total of 10 electrons, but I need to draw 11. So I've maxed out that first orbit. I've maxed out that second ring. I'm going to move on to the last one and draw my 11th electron. That last ring can also hold a max of 8. And then you just keep going. That's really the order. The first ring is odd because it can hold only 2, and then every other ring after that is 8. So this is what a sodium atom looks like that is neutral. Now, what sodium tends to do in reactions is it likes to have full rings. And as you can see on this outer ring, it is definitely not anywhere close to full. So what it would like to do is get rid of that outer electron so that it has just this interior ring that's a perfectly full ring. So sodium will lose 1 electron in a reaction. It'll give an electron away. And that'll change the structure of sodium. Sodium is still going to have an atomic number of 11. So it's still going to have 11 protons in the nucleus. But since it lost an electron, my electrons are going to look a little bit different now. Instead of having 11, I'm going to have 10. So I'll have a max of 2 in that first ring and a max of 8 in that second ring. But that'll work out perfectly because I've drawn a total of 10 electrons, which is all I have now. But this is going to affect the overall charge of this particle. Instead of having 11 negatives, now I only have 10. But I still have all 11 protons, so I still have 11 positives. So this particle is no longer neutral. It has a net charge now because the protons and the electrons do not balance out. Now, 11 positives and 10 negatives is going to produce an overall positive charge. We call ions that have an overall positive charge cations. So an ion of sodium is going to be a positive ion or a cation. So we're going to look at a different example of what happens when atoms give away or take electrons. Before I move on to the next slide, though, what I think that you need to highlight, what you should highlight, is that positive charged ions or cations, they're formed by losing electrons. They could lose 1 electron or 2 electrons or 3. It doesn't really matter. When you're losing negative electrons, you're going to become more positive. And I think of it kind of like if you're losing negative people out of your life, if you have negative friends or negative Nancys in your life and you lose them from your social circle, you become a more positive person. Atoms are the same way. When they lose their negative charged electrons, they become more positive. So they form cations. We're going to look at an opposite example with chlorine. So chlorine is element Cl. There we go, element Cl, and it is element number 17. It has an atomic number of 17, which means that it has 17 positive protons in the nucleus. Now, an atom of chlorine is going to be neutral. So down here, I'll write out my charges. It's going to be neutral. That means it has 0 charge. So it has 17 positives. So in order to be neutral, that means it must also have 17 negatives so that the positives and the negatives balance out to neutral. So when I fill in my electrons, I have to remember I can have a max of 2 in that first ring, and then every other ring has a max of 8. So I've drawn 2, 4, 6, 8, 10 electrons, and I've maxed out that second ring, so I'm going to move on. 12 electrons, 14 electrons, 16 electrons, 17 electrons, and I got really close to filling up that outer ring, but I didn't quite fill it up. In fact, I've got room for one more electron, and you might even see it with the pattern that I did. Right here, I've got space for one more electron. Now, a chlorine atom would like to have a full outer shell, a full outer ring. So what chlorine is going to do during a reaction is it is going to gain an electron. So instead of losing, it does the opposite of sodium. It gains electrons during a reaction. Now, this atom in particular only has space for one more electron. So chlorine only gains one more electron. So when I gain one more electron, the identity of my atom is still chlorine. That means it's still element number 17, which means it still has 17 protons. But my number of electrons has changed now. So if I used to have 17 electrons and I gain one, now I have 18 electrons, which is 18 negatives. So I'm going to draw my electrons and I'm going to add one extra electron. So I've got a total of 10 that I've drawn. I'm at 12, 14, 16, and 18 electrons. So now I'm going to look at my charges and see what's the net charge going to be on this particle. So I know I have 18 negatives because I have 18 electrons, and I have 17 positives because I have 17 protons. These do not balance out. So instead of having a neutral particle, and instead of having a positive particle, in this case, I have a negative particle. We can call it an ion since it has a charge. So since this is negative, we can't call it a cation anymore. We use a different name entirely. We call it an anion. Anions are negative ions. So what I need to associate in my brain, I'm going to highlight this, is that negative ions are called anions, and they're formed by one thing and one thing only, by gaining electrons. It doesn't have to be one electron, it could be more than one, but if electrons are gained, that atom is going to become negative. And you can think of it with the same analogy we had before. If more negative people come into your life, more complainers, whiners, negative Nancys, they're going to bring you down. They're going to make you more negative. And atoms are the same way. If they gain negative electrons, they themselves become more negative. So if we were to wrap this up with a nice, neat definition of what an ion is, we could say that an ion is a particle with a net charge. It could be positive, it could be negative, but as long as it has a net charge, it is called an ion. Now, we could be more specific and talk about types of ions, which we've already mentioned. Neutral means it has zero charge, and we call these particles atoms. So if you're looking at a particle that is neutral, you wouldn't call it an ion at all. You'd say that's an atom. Particles that are positive, we can call ions, but specifically we can call them cations. And you might be looking at that picture and thinking, that kind of reminds me of something. A good trick to remember that cations are positive is that cats have paws. They are positive. Anions are negative charged ions. And I don't really have a good way to remember anions other than it's spelled just like onions. It just has an A in the very front instead of an O. And onions make you cry, and that's a negative thing. That's a sad thing. So anions are negative. Now, there's one other type of ion that I haven't mentioned so far, but we'll see it in the future. A polyatomic ion is an ion made of multiple atoms. Now, you might be thinking, aren't atoms neutral? They are neutral, but when you get certain atoms together in a group that we call a molecule, that molecule can sometimes have a net charge to it. So, for example, there is a molecule called ammonium that consists of 1 nitrogen and 4 hydrogens. Makes a pretty structure like this, kind of like Mickey Mouse if he had 4 ears. And overall, this molecule has a charge of +1. We call it polyatomic because poly means many and atomic means atoms. So this is an ion made of many atoms, made of more than 1 atom, whereas a cation is usually just referring to 1 atom, and anion is referring to 1 atom normally. As we can see in our drawings up here, for chlorine and even for sodium, we had 1 atom that was gaining and losing electrons that formed an ion. Polyatomics are just a special type of ion because it's multiple atoms getting together to form a net charge. So hopefully this helps with differentiating the difference between an ion and an isotope.